Welcome to this continuation of the security part of the communication chapter of the Smart Grid course. The plan for this week, today we'll roll together to continue the lecture on security. After the lecture, I invite you to take the quiz. As usual, the quiz is intended to reinforce and test your understanding of the lecture, and to prepare you to the lab for those who do the advanced lab, and to prepare you for understanding security in general. And the lab is due after the Easter break. Last week, we discussed encryption as a mechanism to hide a text so that attackers who see the text, who see the encrypted text, cannot gain any information about the message. We've also seen that this is providing one part of the security. Another part of the security, the authentication, is provided by an additional mechanism. For example, a message authentication code that computes a tag that is added to the message and prevents an attacker from forging the message, transforming the message by getting it online and intercepting the message, modifying it, and sending it to the destination. We have seen also that it might be difficult to do a tag. You need to be careful that collisions are very hard to mount. Collisions mean being able to modify a message and know how to modify also the tag. And one way that is one of the standards today is to use an encryption mechanism in chaining mode, for example, AES, and we obtain the so-called CBC MAC that takes a message, breaks it into blocks of 128 bits, because the size of the blocks of AES uses the size of the message as initial part, a plain text that is encrypted using AES, K is the key. Then we obtain a first block that is used again by XORing with the first part of the message, and etc. Until at the end, we obtain just a little block of 128 bits, which is the tag. This is where we finished last week. For example, if I send this message to my bank, bank transfer, then the AES CBC MAC would add a 128-bit tag, which is a chain of hexadecimal digits that would look like this here. And if I change anything in the text here, then it is very unlikely that I am able to compute the resulting tag. So the tag here would be modified if I change anything, should be modified, but if I don't have the secret key, I cannot modify it here. So this is how it works. That's the integrity part of the tag. Now, a MAC is not designed to provide confidentiality. We need to transmit the message here. Here it's transmitted in the clear, so anybody can see it. The tag alone cannot be used to recover the message. If I send to you only this tag, only this 128 string, you're not able to reconstruct the message. Why? Well, essentially, because the tag is usually much shorter than the message. So there are more possible tags than there are possible messages. So at least in theory, it is not possible to reconstruct the message from the tag. In specific cases, if you have a short dictionary of possible messages, then it might be possible to reconstruct the message from the tag if you have a library of known messages and tags. But that is, in principle, to be avoided. This means that if we want both confidentiality and integrity, we need to have the two together, side by side. We need to combine encryption and MAC. For example, if I have a message here, I can encrypt it. I obtain the cipher-text using what we saw last week. I can also compute a tag, and I will obtain a tag. I transmit both the cipher-text and the tag. The tag will prevent the message from being tampered with, as we have discussed. But only the cipher-text will be transmitted, so an attacker will not see the clear text, so that provides some fairly strong security. You have variants of this. For example, you could first compute the tag, then add the tag to the message, and then encrypt it. Now, the receiver must have both the decryption key, which is the same as the encryption key, and the tag key, capital L. So the receiver will need to first decrypt the message, then the receiver will receive the plain text plus the tag, then will verify the tag with the key L. That's the second method. Another method changes the order. First, you encrypt the message, then you put a tag to the encrypted message, and you transmit both the encrypted message and the tag, like in the first case. In order to check and understand the received message, you decrypt the message, you obtain the clear text, but you verify not the clear text with the tag, you verify the encrypted message with the tag. So all those combinations exist. Now, it turns out that there are attacks against encryption mechanisms that consist in sending chosen ciphertext. What is chosen ciphertext? Well, it consists in manipulating the ciphertext and observing the response of the decryption system. The decryption system typically sends error messages, and in the past, our colleague Serge Bonnet at EPFL has demonstrated that AES-CBC could be vulnerable to such attacks. So if we can freely choose the ciphertext and submit it to the decryption mechanism, then you will gain some information, which in some specific cases and with a lot of computing resources could help the attacker break the encryption here. Now, in order to make this impossible, out of these three combinations, there is only this one that prevents this, because in this third combination, we verify the encrypted message. So if the encrypted message has been tampered with, which is what the attacker will do in the other systems, you send wrong encrypted messages and look at what are the error messages that are sent by the destination. Those two combinations do not prevent this from happening. So they don't protect you against such attacks. Of course, we will not discuss the details of such an attack, but that gives you a flavor of the type of things that you'll be careful with when you design or implement cryptography or encryption system. So the take-home message here is, if you have to implement an encryption or a tag system in a project, then don't do it. You should only implement things that have been implemented and checked by the whole security community. And there are standards for this. So there are standard and open implementations that have been listed, in particular on the NIST website that lists all the secure encryption and authentication systems. For example, here, the internet standards, the RFC, we followed by a number that means internet standards, give exactly what we should do now. For example, if we use TLS, which is one of the mechanisms that's often used in the context of smart grid for encrypting TCP-IP messages, then this standard specified exactly how to do the combination of encryption and authentication. Well, a quick recap at this point. We're just halfway through the set of mechanisms. So the first two mechanisms we've seen is MAC and encryption. MAC uses a secret key known by sender, produces a tag. The tag is sent in the clear text. And a secure MAC means that it's not possible to forge a tag. And a MAC can be derived from encryption, typically, but there are also other mechanisms we'll see. And MAC alone does not provide confidentiality, therefore you need to combine them together. Little quiz to check your understanding. What do you think about the secure MAC? I close the poll in a few seconds. The majority says A, but the correct answer is B. So a passive adversary is an adversary that simply observes the messages. So a passive adversary cannot be detected by its direct action. It can be detected or suspected if something bad happens. You can think that somebody has spied on you, but it cannot be detected in the sense that it does not modify the message or does not send to you corrupt messages, artificially generated corrupt messages. So of course, the goal of a MAC is to protect you against active adversaries. Those are adversaries that would change the content of the message. So that the answer is B. And of course, it does not provide confidentiality, so C is wrong.
Sorry?
Yes?
If you don't have confidentiality, how can it be secure against passive adversary?
Well, of course, it is not. That's a good question. So there's perhaps an ambiguity in the question. Of course, implicit here is a secure MAC guarantees in the sense of authentication. A secure MAC cannot guarantee confidentiality. Right? So it guarantees integrity, and the integrity is protected against passive and active adversaries. Guaranteeing integrity means guaranteeing that the message that you receive is indeed the message that was sent by the sender, known to you. The sender known to you being the other guy who has the secret key that you're using for verifying the MAC. That's all that it guarantees. It does not guarantee, of course, confidentiality. That's point C, right? It does not guarantee confidentiality, but it guarantees integrity, and it's secure in the sense that the integrity is guaranteed against active adversaries and passive as well. Passive adversary would be an adversary that simply observes the messages and tries to infer something about the content of the message. But in the sense of integrity, if you want to attack against the integrity, at some point you will need to be active. Good. Next question about the CTR and CBC modes of operations of AES. I close in a few seconds. The majority says B, which is true, but A is also true. So the correct answer is C. The CTR and CBC modes of operations of AES, if you remember, that's a mechanism where we add a nonce, which means a number that is different for every block, because AES builds encryption on blocks of 128 bits. So by chaining or using the counter mode, we are able to encrypt messages that are longer than 128 bits. So that's part A. But if we do that, we have seen that if we don't use nonces, the same block is always encrypted to the same cipher-text. And since it is very likely that in computer messages, there are blocks that would always be the same, for example, because they are MIME headers or PMU protocol header types, so they are completely predictable. So this would give opportunities for an attacker to create what is called chosen plain text attacks. And the goal of the CTR and CBC modes is to prevent that. So that was just a reminder of what those terms mean. So the correct answer is C. Well, we've done a quick survey of two essential building blocks of security, of cybersecurity, which are encryption and authentication. But those two mechanisms have a big drawback, is that they require keys to be shared between the two ends. Right? So if I want to go to my bank and do a private transaction, I need to have a secret key with my bank. So how can I do that? Well, I could use special out-of-band mechanisms to agree on a key that I will send using a very secure way with my bank. It's possible, but that's very, very complicated. So this is not scalable. If we want to have encryption everywhere, like we should have in any computer network, we have the problem of how to generate and distribute the keys. And of course, the keys must be distributed in a secure way. So we have, in some sense, the chicken and egg problem. If I receive a message that is verified by a MAC, the only thing that I know by checking the MAC is that whoever wrote this authentication tag has the secret key. So the guarantee is only that. So I must also guarantee that only the intended sender has the secret key. So the key, having the correct key, is part of the authentication. So what happens in particular if A and B do not trust each other? For example, if you are a website that provides some information like the price of selling some product or the time of opening of some service, you want that this information is authenticated for your customers. You want to make sure that if you go to a certain place and you buy things for a certain price, the price is the one that you see, because otherwise you might be some cheating is possible. But of course, if you're a merchant, you don't trust all the people who come to your site. So what if A and B do not trust each other? For that, symmetric cryptography does not provide a solution, because symmetric cryptography always requires that the two ends know the secret key. But there is a silver bullet, there is a magic thing called asymmetric cryptography, also called public key cryptography, that solves the problem. With asymmetric cryptography, the keys are not the same on the two ends, so for encryption and decryption. So asymmetric cryptography provides the same type of functions as symmetric, encryption and authentication, but they have different names. So asymmetric cryptography encryption is typically called public key encryption, and when it's used for authentication, it's called digital signature. So this is what we will discuss now here. So public key encryption. Public key encryption is the same as asymmetric encryption, and it simply means, like before, I have a message to send. I want to hide it from any attacker that can, any here passive attacker that can spy on me. So I encrypt it with a key, and whoever receives it will decrypt with a key also. The difference here is that the key used for encryption is different than the key used for decryption. And one of the keys, typically here the encryption key, can be made public. Made public means it's not secret. Anybody can know it. Here the decryption key is private, which means that only, private here means secret. That means only the intended recipient will be able to decrypt. So that provides protection against confidentiality, because an attacker here will very well know the public key. That means the attacker can forge a message if they want, but they cannot understand this message that was sent by the guy on the left here. The message that was sent that's intended to me, for example, cannot be read by anyone else than me, because I am the only one having the private key. So as we saw, it should be practically impossible for somebody who reads the encrypted text and does not know the private key to decrypt and know what the plain text was here. Similarly, it should be impossible. So that's the first thing. The second thing is, of course, it should be impossible or practically impossible to recover the private key from the public key. The keys obviously must go by pair, right? The private key goes together with a certain public key because that's the public key of me, for example, if you want to send me a message. And the public key being public, of course, all attackers in the world will spend all their computing resources trying to guess what the private key is from the public key. And that should be also, that's another required property, which, as you understand, is much more difficult than what we have for symmetric key cryptography. It must be impossible to do this kind of attack. The first type of asymmetric cryptography system is RSA. It was developed in 1977. RSA are the three initials of the authors. And this is what really has completely changed cybersecurity. Of course, in 1977, the internet was not very public. There were very few people who were using computer networks. But that really made the difference. And that seems really magical. This is what has enabled the internet to become a system where we can do things like banking, for example. How does it work? RSA is based on properties of arithmetic, modulo arithmetic, prime numbers, that kind of stuff. It uses first an exponent, which is public. It must be a power of 2 plus 1 for some reasons that we will not discuss, and it must also be a prime number. Now, the good news is there's lots of numbers of this type. For example, we could use this one. Having an exponent of this form has a lot of benefits. When we compute modular arithmetics here, the computation may, depending on what you do, may take some time. So the computational costs of things like RSA is not minuscule, right? It takes considerably more time to encrypt using RSA than using symmetric key cryptography. The form of this number is an optimization because when you need to, as you will see, you will need to compute things m, for example, to the power e. Exponentiating something that's a power of 2 is done in a number of steps that is order of the exponent and not the number itself. Because if you square something, then you obtain the power 2. If you square it again, you obtain the power 4. If you square it a third time, you obtain the power 8, etc. If you do it 16 times, you obtain this number to the power 2 to 16. So computing m to the power 216 means squaring it 16 times and not doing an exponential number of operations. So that's reasons of that nature that causes, that justifies requirements to have things of this type. So that's a constant of the algorithm. The public key here and the private key are derived from two prime numbers. So the private key is a pair of two prime numbers. Of course, the prime numbers must be large because if you choose a prime number like 3, 5, or 7, a small one, then the attacker, using a brute force attack, trying all the possible keys, will break your cipher. But there is, as you may know, there's an infinite number of prime numbers, and it's so you can always choose prime numbers that are arbitrarily large here. So that's the private key. You pick two prime numbers, and today, for RSA to be secure, we need that the numbers of the order, each of them are the order of 1,000 bits. So they are huge numbers here. And you keep them secret. And the public key is simply the product. That seems a bit strange, but the key thing is that, at least today, as long as we don't have quantum computers, factoring a number capital K into its two prime factors here is a problem that's extremely hard. So we don't know how to do it. There are small optimizations, but essentially it's not much better than doing by brute force. Now, if each of the factors have 1,000 bits each, then you need to combine all the combinations of 1,000 bits, which is a truly astronomical number that even all the computer power of the world is not able to break. As long as we don't have quantum computers. We'll talk about that a bit later. So this is my public and private key combination. Now, how does it work? Well, if I have a plain text, first I map it into a sequence of integers modulo k. So I do modulo k arithmetic, which can be done because k is public. And the encryption consists in taking a message m, putting it to the power e, exponentiating to the power e, and taking the modulo k. The decryption is difficult if you don't know how to factor k, because this is an exponentiation, and what is known as number theory is that doing the inverse of an exponentiation in modulo arithmetic is a very hard problem. That's called a discrete logarithm problem. If I give you m to the power e modulo k, and you don't know m, you know e, and you know k, but if you don't know m, the best thing you can do is to try all the possible m's and do the brute force. It's quasi the only solution that is known today. Except if you know the factors p and q, if you know how to factor the number capital K, there is a theorem called the Chinese remainder theorem that says that if you take the ciphertext C, there is a magic number f such that if you do c to the power f, you obtain exactly the number m here. But in order to compute f, you need to take the inverse of e modulo the, roughly speaking, p minus 1 times q minus 1 here. So if I know the two prime factors pq, which means if I know the private key, I can compute p minus 1 times q minus 1, and I compute the inverse of the exponent e modulo k. So in some sense, f, which is put in red here, is part of the secret key. And it is believed that when the integers p and q are very large, computing f is very difficult. The only known solution when you don't know p and q. But if you know p and q, of course, that's easy, because computing an inverse is a quadratic time algorithm. That's the Bezout algorithm, which you might know from high school. So computing an inverse modulo something is very easy. So I know f, and then by exponentiating to the power f, I will decrypt the message. So that is the principle of RSA. And to give you an idea, the numbers that you have are numbers like this, right? This is perhaps my public key. And the question is, can you factor out this public key? And of course, we don't know efficiently how to do this other than by first factoring the modulus capital K into prime number. Let's do a toy example to check how it works. I will use e equals 7. So 7 is also a prime number. Is very small. It doesn't have the form that I gave before, but it's a very small number that helps us do the thing easily. And the public key is 33. Right? So those are decimal numbers here. Then the private key is a factoring of this, 3 times 11. Of course, that's a stupid example. The private key is derivable from the public key in a very easy way. But as I said before, if K is a key like this one, if that's your capital K, finding the P and the Q is another story. So here I know P and K secret. Then I compute P minus 1 times Q minus 1. That gives 2 times 20. To be a bit simpler, we can just the least common multiple, that gives 10. So the magic K is 10, and the magic decryption exponent is the inverse of E, the exponent 7, which is public, modulo this 10, which is secret. So what is the inverse of 7 modulo 10? Well, it is 3, because 3 times 7 gives 21. 21 modulo 10, modulo means the remainder in the division by 10, then it is 1. If I divide 21 by 10, I obtain 2 times 10 plus 1, so the remainder is 1. So being the product EF is 1, that means F is the inverse of E. So the magic number, which in theory should be very hard to obtain from K, from capital K, is 3, but very easy to obtain if I know that K is equal to 3 times 11. So the decryption exponent is 3. We can check, for example, if I give you a plain text like this one, B is translated to a simple coding by the number of the letters and the alphabet. A is mapped to 1, B to 2, etc. That's ad hoc code. In reality, we use typically more sophisticated translation of letters to numbers. The plain text is the sequence of numbers, here written in decimal. The cipher-text is made of every number here modulo 33, because 33 is the public key, to the power 7. So you take 2 to the power 7, you take the remainder modulo 33, you obtain 29. The remainder modulo 33 is a number between 0 and 32. And then that's the ciphertext. That's the text that will be encrypted. Of course, if I have the plain text, I'm able to write the sentence that was sent very easily. In order to obtain the cipher, to decrypt, I simply multiply to the power 3. For example, here, if I have received 10, 10 to the power 3 gives me 1000. 1000 modulo 33, the remainder happens to be exactly 10. So we see that taking the number back to the power 3 gives us exactly the same original plain text here. So I can decipher if I know the private key. What I've shown is RSA, which is working today, as I mentioned, only if the key is very, very large. So RSA tends to be replaced today by other systems that are using similar mechanisms, but not prime numbers. Instead, they use, for example, elliptic curves that in that case require keys that are much smaller. So elliptic curve cryptography is a variant of number theory that is more difficult to explain. I could explain RSA in one slide. Elliptic curves would take more time, so we won't do it. But it's similar number theory kind of algebra that is used. Elliptic curves and RSA are not what is called quantum proof. As you may know, there is a tendency, there is a thrust in the computer industry to develop what is called quantum computers. Quantum computers are based on quantum physics, and it is believed that if they become large enough, they would be able to solve problems that require exhaustive search. Essentially, with quantum computers, you can have huge amounts of parallelism, and then it makes it possible, for example, to break the factoring problem. If I give you a large K with a quantum computer that is also large enough, I could very easily break it into its prime numbers, prime factors here. Quantum computers are not a threat today because they are very small, but there is a risk that sooner or later industries like IBM or others, or hackers or countries develop technologies with quantum computers that would be able to break problems that are at the root of RSA or elliptic curves. So there is now a research into doing alternatives to RSA or ECDSA, elliptic curve cryptography, that is quantum proof. And this is, for example, lattice cryptography. Lattice cryptography is similar, but is believed today to be not crackable with quantum computers. So as you see again, if you want to be secure, you need to follow what the instructions of entities like NIST or the security specialists say, and always use the latest state-of-the-art encryption or authentication system. Now, all forms of public key cryptography are computationally much, much more expensive than symmetric key cryptography by several orders of magnitude. So that is a problem. If we want to transfer PMU messages and we need to encrypt every PMU message with public key cryptography, It is possible in some cases, and one of the PhD theses of EPFL a few years ago addressed this problem. So it is possible, but it requires essentially a PhD thesis. It requires a lot of work, and it doesn't solve all the problems. It's not always applicable. So when you go to your bank to do a transfer of money or to just read your bank statement, you will typically not use public key cryptography for everything. Instead, we will use what is called hybrid encryption. The idea of hybrid encryption is very simple. We use public key cryptography to generate one secret key on both ends. So one secret key that will be used by me and my bank, but will be used only for the duration of our transaction. If I remain idle for some time, you will notice that when you don't do anything on your bank, on your e-banking connection, after some time it breaks and the bank requires you to authenticate again. This is because it is using, or among other reasons, because it is using a session key, so a secret key that will be valid only for a short amount of time and will be stored only on temporary storage. So it's data that will be deleted and that hopefully is not logged. The benefit of doing that is that the transaction will be using the symmetric encryption. That means it will be very fast. If we would not do that, then going to the bank would mean every transaction you do, you would have a very large response time. So that would be a problem, and that would also be a problem for the user not being sure whether the bank really works. When you click for a transfer, then you wait for some time for it to happen. That would be also a problem for the server, because that means the server would need huge computing resources here. How does it work? Well, when you connect to the bank, you know the public key of the bank, and the bank, of course, knows a secret key, its secret key here. Then your browser will compute a random key here with no specific meaning to this key. So using true random numbers, random number generators, it will create a random key, L, here. Then of course, this is the key that will be used for encryption using AES, right? When I will send a message to the bank, I will encrypt it with AES, for example, with CBC chaining. So this key must be kept secret here, but now I need to send it to the bank. How do I send it to the bank? Well, I encrypt it using the bank public key, and what I send, Y here, contains the encrypted secret key. So the bank is able to decrypt, and this is possible only by the bank. So any attacker in the middle will read Y, but will not be able to infer the value of L, the secret key that we will later use. This will take some time, but this is okay because that's when you set up the connection, when you do the authentication transaction with your bank. And once the secret key here is received by the bank, both parties now know L, and you can use AES to decrypt the message here. So this is used everywhere in web browsers or in PMU encryption because this is much more convenient and doesn't load the CPUs of the devices here. Voila, this is how hybrid cryptography works. Now a little quiz. PMU sends a confidential message to PDC using asymmetric cryptography. What key should be used by PMU? I close the poll in a few seconds. And the majority says A, which is wrong. So PMU sends a message to PDC, and PMU wants this message to be confidential. So confidential means I want only PDC to be able to see the content of the message. So if I encrypt with my public key, with PMU public key, who can decrypt it? Only me, because only PMU owns PMU's private key. So if I use my public key to encrypt, nobody other than me can decrypt. So of course it will be confidential, but it will also be useless because nobody can decrypt. You want the PDC to decrypt. So you should send with the public key of the PDC, which you can, because by nature, a public key is public. So anybody can know what is the public key of the PDC. So answer A does not work. So A does not work. C works. If I send with a PDC's public key, if I encrypt with a PDC's public key, everybody can do that, by the way. But once the message is encrypted, then somebody who sees the encrypted message cannot understand what the message is, cannot decrypt, except if you know the private key, and that is in principle only PDC. If I send with my private key, then that's perfectly useless because anybody, so if I send with my private key here, anybody can decrypt, because in order to decrypt, we can use a public key. And this I haven't mentioned, but encryption and decryption are symmetric. If you encrypt with one key, you can decrypt with the other. So if I send with my private key, then anybody can decrypt, and that's also useless. It is not at all, it's useless in the sense of confidentiality. So the correct answer is C. Same thing, D is not possible, because if I don't know the PDC private key, of course. Okay. Another question. In a substation, I have capital N devices that should be able to communicate directly and securely with each other. As you know, substations are typically not manned, which means there is nobody in a substation. If an attacker wants to come, and they just monitor when is the substation receiving visits from maintenance or operators of the company, it's very easy to learn by spending a few days around the substation. So if you manage to come on at a day where nobody is in the substation, then you can very easily get into it, and you put packet sniffers like you're doing in the lab with Wireshark, and you can observe all the traffic here. So if we want to prevent this from happening, and we use symmetric key cryptography or asymmetric key cryptography, how many keys should be stored in total in the system? I close the poll. And the majority gives the correct answer. Whoops. With asymmetric cryptography, every device needs simply a public-private key pair. So you need one such private key pair per device, and then all other devices can send encrypted information to every device. But for symmetric cryptography, you need n times n minus 1 over 2. You need one secret key per pair of devices, which is order of n squared. So that's the gain. If you have 100 or 200 devices in a substation, then you have a gain from 100 to 10,000 keys. But even 100 is a lot. So we will need other mechanisms. We will need what is called certificates, which is what we will discuss in the next part of the lecture. But right now, let's do a break and let's resume at 10:15.
Sorry?
Yes, question?
Yes, I don't understand. I answered the H. I don't understand why it's F. Could you explain again, please?
Well, with asymmetric cryptography, public key cryptography, every device needs simply a public key, private key pair. It's like in the previous quiz. For a PMU to communicate with a PDC, the only thing that the PMU needs is the PDC public key, and the PDC needs the PDC private key. So for private communication between anybody and the PDC, we need only one key, which is the PDC public key, private key pair. Right? Similarly, if the PDC wants to send confidential information to a PMU, it needs the PMU public key and the PMU needs a private key. So if all device wants to communicate with all device, we need that every device has two keys, a pair of private and public keys with asymmetric cryptography. Here, of course, I'm assuming everybody wants to communicate with everyone with confidentiality. In contrast, if we use symmetric cryptography, when PMU1 talks to PDC, both need a secret key. Then PMU2 talks to PDC, they also need secret key. Now, of course, you could say you could give the same secret key to everyone, but that is very bad security practice, right? The goal of a secret key is to be secret. If all PMUs have the same secret key for communicating with the PDC using AES, for example, then when the PDC receives a message, it doesn't know whether it is truly encrypted by PMU1 or PMU2. So if any single PMU is corrupted, the entire system gets corrupted. So the principle of symmetric cryptography requires that the secret keys are secret. So only two ends know the secret key. If there are n square pairs of communicating device, each of these pairs need their own secret key pair. So in AES, the key should be per channel, not per, so per channel, that means per pair of communicating entity. Does that answer your question?
Yes, thank you.
Good, if there are other questions, don't ask to hesitate. I will turn the camera off if there are no more questions now, but I am online, so don't hesitate.
I'm sorry?
Yes.
I have actually a question for slide 41 on hybrid encryption. I just wanted to understand better. You said that it's limited in time due to this authentication purposes. But has it something to do that the time that our connection is valid, I mean our shared key L is valid, is less than the time it would have taken for a third party, like a malicious third party, to decrypt, to find out this key, or nothing? It has nothing to do with that.
It's a very good question. Yes, I did not discuss this, but you gave exactly the question and the answer. So symmetric cryptography, schemes like AES, the security becomes weaker if you use the key for a huge amount of messages. If you use the same key for years, then an attacker that has observed as the logs of all your conversation for years might get some information that, together with other computer hacking mechanisms, could help accelerate the time it takes to guess the key. So that is one of the aspects. So therefore, you want to have session keys that don't stay valid for too long. So that's
cool.
one argument. But another reason also is that this key should really be made secret. That means it should not be stored. Should not be stored on your permanent storage on your computer, nor on the server computer. Because if it's stored somewhere, a virus or some infection of your machine could get the keys as well. So another reason is to really make it temporary. So as long as your computer, if you close your browser, for example, you don't want that the key is kept in information that is stored on your computer as part of the browser information.
Okay, thanks a lot.
You're welcome. So I will close the camera. If other questions come to your mind, don't hesitate to ask or in the chat. I'm still remain online. So see you after the break.